University of Penn engineers have achieved a breakthrough in quantum networking by successfully transmitting quantum signals over Verizon's commercial fiber optic network using standard Internet protocol. This marks the first demonstration of quantum data transmission on live commercial infrastructure, published September 25th in the journal Science. The experiment utilized a custom silicon chip, dubbed the Q-chip, to coordinate quantum and classical data streams over a 1-kilometer stretch of Verizon's campus fiber network in Philadelphia. The system maintained transmission fidelity above 97%, demonstrating that fragile quantum signals can coexist with everyday internet traffic on existing infrastructure. This breakthrough represents a significant step toward practical quantum internet development. The revolutionary Q-chip technology enabled this quantum networking breakthrough. The custom silicon chip coordinated quantum and classical data streams over Verizon's live commercial fiber network, maintaining transmission fidelity above 97% while demonstrating that fragile quantum signals can coexist with regular internet traffic on the Q-chip's design, allowing it to function within existing commercial infrastructure rather than requiring specialized laboratory conditions. This demonstration on Verizon's Philadelphia campus network shows that quantum communication can be integrated into real-world networks that experience the normal environmental variations and traffic patterns of commercial operations. This success of the experiment suggests that quantum networking could be deployed much more rapidly than previously thought possible. The breakthrough centers on a train and cargo approach to data transmission. The Q-chip pairs quantum information with classical optical signals that act as navigational headers, with the classical signal traveling just ahead of the quantum signal. This allows researchers to measure the classical signal for routing information while leaving the quantum information intact. The classical header can be measured and managed without disturbing the accompanying quantum states essential for secure communication and quantum computing applications. This approach enables quantum data to be packaged into standard internet-style packets and routed using the same addressing systems that connect everyday devices online, creating a pathway for integrating quantum communication into existing network infrastructure. Unlike laboratory settings with controlled conditions, commercial fiber networks face constant environmental variations from temperature changes, vibrations from construction, and seismic activity. The Penn team developed an innovative error correction method that uses the measurable classical signal to infer necessary corrections for the quantum data without directly measuring it. This approach overcomes the significant challenges of maintaining quantum coherence in real-world environments. Where laboratory experiments occur in isolated, controlled conditions, commercial networks must handle mixed traffic and environmental instability. The successful demonstration on Verizon's network shows that these challenges can be overcome, opening the door to practical quantum networking deployment on existing infrastructure. The Q-chip silicon-based design and compatibility with established fabrication techniques position it for mass production, potentially enabling rapid scaling across existing fiber networks. As Professor Liang noted, all you need to do to expand the network is fabricate more chips and connect them to existing fiber optic cables. This manufacturing advantage represents a significant departure from previous approaches that required specialized quantum-only infrastructure. The compatibility with standard silicon fabrication means that production can scale quickly using established manufacturing processes. This approach dramatically lowers barriers to deploying quantum networking at scale compared to building specialized quantum-only infrastructure, potentially accelerating the timeline for practical quantum internet development by years. This practical demonstration represents a significant advance over previous quantum networking experiments that required specialized laboratory infrastructure or dedicated quantum-only networks. By showing that an integrated chip can manage quantum signals on a live commercial network using the same protocols that run the classical internet, the Penn team has taken a key step toward larger-scale experiments and a practical quantum internet. The ability to use existing commercial infrastructure rather than building specialized networks dramatically reduces the cost and complexity of quantum internet development. This breakthrough suggests that quantum networking capabilities could be deployed incrementally alongside classical internet infrastructure, following a similar evolutionary path to the development of the classical internet itself. The successful demonstration of quantum signals on commercial networks opens the door to numerous practical applications, including quantum cryptography for unhackable communications, distributed quantum computing by linking quantum processors over distance, network synchronization with ultra-precise timing, and quantum sensing through distributed measurement networks. Next steps include extending the transmission distance, increasing data rates, and demonstrating multi-node quantum networking on commercial infrastructure. The integration of quantum capabilities into existing internet infrastructure represents a paradigm shift in how we approach the development of quantum networks. Rather than building separate quantum infrastructure from scratch, this approach enables the evolutionary development of quantum capabilities within existing networks, potentially accelerating the timeline for practical quantum internet development significantly.